Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. In our last lecture, we were discussing the I/O interface with the CPU. Now we discussed at length how to interface the peripheral devices and have a connection with CPU. With the CPU, we said that the I/O devices could be either memory mapped or non-memory mapped. The devices could have a shared bus with the memory subsystems, or we could have a separate I/O bus. In any case, the requirements of the I/O subsystems in some ways resemble the memory subsystems, and in some cases, these requirements differ. In other cases, there are differences, and these differences originate from the fact that I/O devices have a varied speed requirements. Now, the similarities in terms of the decoding process are similar. We discussed, for example, Falcon A processor, the decoders, and we just saw that a decoder primarily is a combinational circuit, and we implemented this particular combinational circuit by an example of using a reference AND gate. The inputs to the decoder are from the address bus, that is the data from the address lines, plus some inputs from the control bus. Typically, from the control bus, we had I/O read or write control signals, or if it is a memory mapped device, then it could be a memory read or memory write. Now, if the peripheral device is an output device, the CPU would provide data on the data bus, and the peripheral device would capture data. It should be ensured that stable data remains available on the data bus for appropriate time so that the peripheral device could capture it appropriately. In case we have an input device, we need to have data isolation. For data isolation, since a number of input devices might be connected to the same bus, one should ensure that when there is no activity, the devices remain isolated. This could be done by using tri-state buffers, and these buffers could be enabled only when the peripheral device wants to send data to the CPU. So the CPU would take the data as input data. We will continue and illustrate the mapping of an input device on the address space for our Falcon A processor, and we consider it with the help of an example shown in the next slide. We need to design a 16-bit parallel input port, and as an example, we map it on address 7E hex for the reference processor Falcon A. The process of designing a parallel input port is quite similar to the design of a parallel output port, except for the following differences. For this example, our address is 7E hex, which is different from the previous value which was used for the output port. Hence, the address decoder in this example would take its inputs from the address lines A0 up to A7. These two, A0 and A7, would be inverted, and others, that is A1 up to A6, would go in a normal fashion. Now the second difference for this case is in control signal. For the output port, we used the control signal as I/O write. In this case, we are going to use the control signal as I/O read. And in the diagram, you see it is written as I/O read with immediate sign, meaning that it is active low. So we need to have the address lines along with the control signal IOR with active low. The next important thing you notice in the figure is that all the 16 lines are isolated by using tri-state buffers. Now, all these buffers are enabled simultaneously, so the enable lines of all these tri-state buffers are connected together, and the enabling signal would come from the decoder. So the decoder utilizes only the low 8-bit address lines from A0 to A7. For this example, we have seen A0 and A7 are inverted and the other one are in true form. The output of an 8-bit AND gate is now connected through another 2-input AND gate. The second input to this AND gate is the IO read signal, the control signal inverted. And then we also see that the output enable is also low active. So therefore we need another inverter at the output of this AND gate. For this particular example, the data would come from the peripheral devices through the tri-state buffers onto the data bus of Falcon A. The data bus of Falcon A is 16-bit wide. It has got 16 lines. We have low significant byte and the higher significant byte. Just for the sake of simplicity, we have simulated the input device by using 16 switches just numbered from S0 up to S15. So if the switch is closed, it would simulate a 1. If it is open, it would simulate a 0. So depending upon whether we want to have any combination of 1 and 0, we just pass on this data from 16 switches to the data bus through the tri-state buffers, and these tri-state buffers would be enabled if and only if our address is correct, and secondly, the IO read is activated on the control bus. In this example, we used the address to which we have mapped the input device as 7E. Now we know that this Falcon A is utilizing two addresses. So the next address 7F would also be automatically skipped, and we can't use 7F for any other device. So if we want to have another device mapped, then from 7E we will just jump on to the next address skipping 7F, and that would become 80 hex. Now, as we discussed in the case of output mapping, we could also utilize the similar concept for IO device, meaning that the total data bus of 16-bit could be separately addressed in two chunks of 8 bits each. So we would like to have one address which is, in this example, 7E mapped for the most significant byte, and 7F would address the least significant byte. And this is illustrated in the next slide. Let us have a look. In this example, we have a 16-bit parallel input port for the same Falcon A processor, now at addresses 7E and 7F hex. The least significant byte is addressed by using 7F, and the most significant byte is addressed using the address 7E. Since Falcon A processor utilizes the big endian convention, note that at the 8 input AND gate, we have moved away the address line A0 and fed it with the IO read after inversion. The address line A0 is as an input to the next two AND gates. One AND gate utilizes it in inverted form and would map the corresponding address as 7E. The output of this AND gate through an inverter enables the top byte, most significant byte, and therefore enables the 8 tri-state buffers corresponding to D8 up to D15. The other AND gate takes the input from the previous 8 input AND gate along with A0 in a non-inverted form, and therefore it corresponds to the address 7F. The output of this AND gate through an inverter enables the lower 8 tri-state buffers from D0 up to D7. Therefore, this implementation independently addresses the least significant byte and most significant byte of the data bus. Let us now consider another example where we combine the two peripheral devices. One is an input device and the other one is an output device. The input device would be simulated by using switches. Let us say we have 16 switches addressed at address 7E, as we have done in the last example. The output corresponds to LEDs. 16 LEDs would indicate the status of the output, and our example goes as follows. We say that the CPU, the Falcon processor, would read the status of 16 switches using an address 7E. So some of the switches might be on, others might be off. After reading the status, it would pass on exactly the same status without any change, utilizing an output address which is DE. In both cases, we utilize the total bus, all the 16 bits together, no splitting, no independent addressing, and the addresses would be automatically aligned. That means the addresses used would all be divisible by 2. Let us see, and we would like to further enhance this example and illustrate by adding up a delay loop, and we would like that the LEDs blink, and with enough time given in between, we would switch on and off each LED so that it appears to be blinking when a switch is on, and the LED remains off if the switch is in off status. The solution for this example is shown in the next slide. As we have said, we are given Falcon A processor with a 16-bit parallel input port at address 7E hex and a 16-bit parallel output port at address DE hex. 16 LED branches are connected to display the data at the output port, and 16 switches are used to send data through the input port. We are supposed to write an assembly program to continuously monitor the input ports and blink the LEDs corresponding to the switches which are set to logic 1. For example, if S0 and S2 are set to 1, then only the LEDs L0 and L2 should blink. If S7 is also set to logic 1 in between, then L7 LED should also start blinking. The solution is very simple. It is indicated in the program shown in the next slide. The first two instructions read the input port at address 7E and send this bit pattern to the output port at address DE. This will cause the LEDs corresponding to the switches that are set to 1 to be turned on. Next, the program waits for a suitable amount of time and turns all LEDs off. Again, it waits for some amount of time, and after waiting, the program reads the input port again. The LEDs that will be turned on at the output port will now be according to the new switch setting, which is available at the input port. The process repeats indefinitely, and this loop is just shown in the corresponding flow chart. It is also possible that we could use a single address for both the input and the output port, which is not done in the previous example. The next diagram shows an address decoder for a 16-bit parallel input-output port, which is utilizing the common address 2C hex for this particular example. The processor is the same Falcon A. The I/O space is utilized using the least significant 8 address lines. As in the previous examples, the most significant bits from A8 up to A15 are not used. Note that now both the control lines I/O read and I/O write are used. This would differentiate which particular register would be written to or which particular tri-state buffers would be enabled. In the diagram, you see the input of 8 input AND gate has a data from A0 up to A7. Some of the lines are inverted, others are non-inverted, which depends on which address we are using. For this particular example, where the address is 2C, you can easily verify after writing the binary pattern that the bits A0, the address lines A0, A1, A4, A6, and A7 would be inverted, whereas A2, A3, and A5 would be non-inverted. The output of this 8-input AND gate is a common input to the next two 2-input AND gates. In the upper AND gate, the second input is the inverted I/O write signal, and the output of this AND gate would go to the enable output of the output port. The lower AND gate utilizes the I/O read signal as a control input, and after inversion, it is fed as an input to the AND gate. The output of this AND gate enables the input port. So therefore, through this example, you could just verify and see that same address is used as an input address for one device as an output address for the other device, but not simultaneously. At one time, only either it would read data as an input from input device, or it would write into the register of the output device. In the previous examples, we have taken up cases where the I/O is non-memory mapped. That means for the Falcon A, we utilized the separate addresses for the I/O. For memory, the address base was different. Now we could also utilize and map these I/O devices as a memory address. Let us look at an example of using the same Falcon A processor. However, we would map these particular devices, whether it is an input or it is an output, onto the same address where the memory was mapped. So this would mean that we would like to use the address space which corresponds to the memory. That could be done also by using the same Falcon A processor. What needs to be changed? There would be a couple of changes. The first one, you can realize that now the address space would be wider. For the Falcon processor, the I/O addressability was from 0 to 255, whereas the addressability for memory utilizes 16 bits. So we need to use all the 16 lines corresponding to the address bus, which would mean we will have A0 up to A15 as the input to the address decoder. So therefore, the address decoder would now utilize all 16 address lines instead of having only 8 address lines. So therefore, as an example, if we want to have address as DE, this would be written as 00DE, and the address decoder would now be a 16 input AND gate, and the 8 higher bits would be inverted and then fed as an input to this AND gate, and it would map an address of 00DE as an example. The second important difference would be that instead of the control lines as I/O read or I/O write, we will use the memory read and memory write as the control signal. The third important change would be that the program would also change. Instead of having the instructions as in and out, we will use the load and store instructions from the instruction set of the Falcon A. Let us have a look at a typical example in the next slide. The figure shows an address decoder for a memory mapped 16-bit parallel output port for the same Falcon A processor. The address to which it is mapped is now 00DE hex and 00DF hex. You would just see that all the address lines as mentioned are used. Since there is a limitation that an AND gate can take only 8 inputs, we use 2 AND gates. The upper AND gates takes from A0 to A7, and A0 and A6, A5 are inverted, others are not inverted, meaning that the address would correspond to DE. The lower AND gate takes the input address lines from A8 up to A15, and all of these are inverted since the corresponding higher byte is 0, 0. The output of these two AND gates are ANDed together and are fed further to the next AND gate, and the control line to this AND gate is a memory write signal with inversion because it is active low. Now the advantage of using the full address range would be that we have a wider range of addressability for the I/O devices. However, the disadvantage is that the address decoder would become more complex, resulting in increased hardware cost. Now in the last example, we have seen that all the 16 address lines were used as an input to the address decoder. Now we could economize if we do not want to use all the address line and have a lesser space. This could be done by using a partial decoding scheme. Take a very simple example. We do have a memory mapped I/O. Nevertheless, as in the case of non-memory mapped I/O, we do not use the upper 8 bits of the address line. So we use only from A0 up to A7 as an input. What would be the result? The result would be that in this case, our total address space would be wrapped around, and this would be wrapped around effect. For utilizing only 8 bits, the wrapping would be after 256. So it would be similar to modulo 256 effect in mathematics, which you know. So this would mean that if we have an address 00DE and another address 01DE, both would be mapped on the same actual address, right? From 0 to 255 would become the effective address space, or we could say that the total address space of which is 64K in Falcon A if we utilized 16 bits of address. However, if the upper 8 bits are just neglected, we don't use these, then the addressable space would become 0 to 255. The next would be again from 0 to 255, and we have all addresses effectively mapped to the same address from 0 to 255. Now, if we want to increase this addressable space, we can do that by including more address lines. As an example, if we do away with top 6 address lines and use the 10 address lines from A0 up to A9, then what would be the addressability? The addressable space in this case would be 1K, and after 1K it would be wrapped around. We will have total 64K divided into 1K of each, and the address would be dictated by the lower 10 bits of the address bus. Now we could economize on utilizing the address space by using a concept of the data bus multiplexing. In the previous example, we just saw that Falcon A has a data bus which is 16 bits wide, and all the 16 bits are transferred to the output or are taken as an input. However, if we divide it into 2 bytes, actually we could transfer 1 byte and indicate it by one address, and independently we could also address the most significant byte by another address. So we would have an addressability for both odd as well as even addresses. And in the case of programming, we would not need to skip the odd addresses. That means the address alignment would not be required, and by multiplexing at one time, we take up 8 bits from the data bus, and in the next reading cycle, we take the next 8 bits from the data bus. This concept is called the data bus multiplexing. Let us see this illustration in the next slide with the help of an example. Consider the situation where an 8-bit peripheral device is to be interfaced with a CPU that has a 16-bit or maybe even larger data bus, but we need a byte-wide address space. Falcon A is a typical example of this particular situation. Each byte transferred over the data bus will have to have a separate address associated with it. For such CPUs, data bus multiplexing can be used to attach 8-bit peripheral devices requiring a block of addresses. Tri-state buffers can be used for this purpose, as it is shown in the diagram. The logic circuit shown is for an 8-bit parallel output port using address DC and DD hex for the Falcon IO space. It is assumed that the CPU allows the use of a part of its data bus during a transfer, and that each 16-bit general purpose register can be used as two separate 8-bit registers. In our previous notation, as we have used, we could define R1L as the lower byte of the register R1, which would be defined as R1 from 0 to 7, and R1H would define the upper byte of the data bus. The LED branches and the 8-bit register shown in the diagram serves as a placeholder and can be replaced by an actual peripheral device in practice. For an even address, A0 is equal to 0 and the upper group of the tri-state buffers is enabled, thereby connecting the data from the bus with bit 8 up to 15 of the CPU to the peripheral, while for an odd address from the CPU, when A0 is equal to 1, the lower group of tri-state buffers would be enabled. This would cause the lower significant byte with bits 0 up to 7 of the CPU to be connected with the peripheral device. The advantage of data bus multiplexing is that all addresses are utilized and none of these is wasted, while the disadvantages are the increased complexity and additional cost of the interface. In practice, if we have an output device, one output address may not be enough. We need to have a series of contiguous addresses, maybe 6 or 8 or even more. Now, the situation would be that if we have, as an example, a printer, we could indicate the interface in the form of a simple block, and this block may contain a number of registers. As an example, let us say we have 4 registers, and each one is 16-bit wide. Now, the addressability is only 1 byte. So therefore, for each address, we need to have 2 addresses for IO interface. So therefore, let us say we have first address as a data in register, first register as a data in register. As an example, we could indicate the addresses as 56 and 57. The next one, we could have another register which would take the control inputs coming from, let us say, from CPU towards the printer. And another 2 addresses would be required for this case, and we will have, as an example, 58 and 59. The next one is another register where we need to have a status, like if the printer has a paper jam, it would be indicated as a status, and We just call this block as a generic I/O interface. So therefore, with the status, we get the status coming from the printer into CPU. The fourth register is indicated as a data in. Now, although for the case of printer, the data would be coming only from CPU to the printer, but as a general case, if it is not a printer or we have both possibilities of getting input and output, we have a fourth register indicated by another two addresses. So therefore, for this generic diagram or generic I/O interface, we have just indicated different possibilities, and you will see that we have one bus indicated as a thick line connecting the actual printer with this interface, and at the bottom, through some address decoding scheme, the input comes from CPU in the form of address bus and the control bus. So using partly some lines from address bus and some from the control bus, the decoder would generate the enable signal or the corresponding clock signals. So having a look at this particular simple representation, we call it as an I/O generic interface for an I/O device. As an example of a generic I/O interface, let us look at a practical example, and that is for Centronics interface, which is very common for the printers. Originally, this was proposed by Centronics, a manufacturer of the printer line, and later on it has been adopted as a standard. Now, this example of Centronics interface is a physical connection between the CPU, or between, you could say, computer and the printer. A cable which is used as a standard utilizes a 36-pin connector on one end and a 25-pin connector on the other end. At one time, we have a parallel transfer of data in the form of bytes. So that means the 8 bits would be transferred from CPU towards the printer. Along with these data lines, we will have a couple of status signals and the corresponding control signals, like to indicate whether the printer is busy or is it ready to accept the data. Or we could also say that we have selected a particular device. So the Centronics standard explains physically which particular lines are connected, are taken as control lines or data lines, or which particular control signals or the status signal are available. Now, you could note that for these data lines, for each data, a twisted pair is physically used, and the twisted pair uses data, for example, D0, D1 up to D7. The second line is grounded, and this would be a digital ground, and also is mostly connected with the physical ground of the chassis. The three signals, strobe, busy, and acknowledge, form a set of handshaking signals. By using these signals, the CPU can communicate asynchronously with the printer, as shown in the timing waveform. When the printer is ready for printing, the CPU starts data transfer to the printer by placing the 8-bit data, which in our example corresponds to ASCII value of the character to be printed, onto the printer data bus. After this, a negative pulse of duration, at least 0.5 microseconds, is applied to the strobe signal. Input pin 1 indicates this particular signal, which is strobe low. It is low active. That means normally it would be high, and when the data is available, the CPU would place a low on this strobe signal. The minimum setup and hold times of the latches within the printer are specified as 0.5 microsecond each, and these timing requirements must be observed by the CPU. That is, the interface designer should make sure that these specifications are met. As soon as strobe low signal is applied, that is, strobe goes low, the printer activates its busy line, which is physically pin 11, and therefore it indicates to the CPU that additional bytes cannot be accepted. The CPU can monitor this status signal over an input port, which would be defined as an address read from this particular port. We will call it as an input or IO status port. When this character is completely received, the acknowledge signal, which is physically available on pin 10, goes low, indicating that the transfer is complete. Soon after this, the busy signal returns to logic 0, indicating to the CPU that a new transfer can be initiated. The busy signal is more suitable for level trigger systems, while the acknowledge signal is better for edge trigger systems. The interface will typically use two 8-bit parallel output ports of the CPU, one for the ASCII value of the character byte and the other for the control byte. It also specifies an 8-bit parallel input port for the printer status to be transferred to the CPU for knowing whether the printer is ready to accept the data or not, or other status signals in the similar form. Let us now use this Centronics interface along with our Falcon A CPU to illustrate the concepts of the interface. When you compare the generic I/O interface, which we defined earlier, with the Centronics interface, you could just see and compare that we have a data register where the data would come from CPU to be printed on the printer. Then we have a control register and a status register. Now, the fourth register would not be used in this case because it is actually a link where unidirectional data would usually be transferred. That means the data would come from CPU towards the printer, and no data would be sent from the printer to the CPU except for the status signal, and for that we have provided a status register. So therefore, three registers are provided: a data register, a control register, and a status register. Each register is 16-bit wide. And in our next example, we want to see and illustrate and explain to you that how the Centronics interface would be implemented. For the sake of simplicity and illustration, we utilize the 6 decimal addresses starting from 56. So 56, 57 for one register, then 58, 59 for the other one, and the third register would use 60 and 61 as the addresses. So we will just call, there are 3 ports or 3 logical ports. We have a logical port indicating data, a logical port indicating control, and the third indicating the status. So let us have a look on this example of mapping the addresses from Falcon A CPU onto a typical printer utilizing the Centronics interface. The Centronics interface requires at least 3 I/O addresses. However, since the Falcon A has a 16-bit data bus, and since we do not want to implement data bus multiplexing to keep things simple, we will use 3 contiguous even addresses, that is, as I said, in decimal 56 onwards, and in hex this would be corresponding to 38 hex, 3A hex, and 3C hex for the address decoder design. This arrangement also conforms to the requirements of our assembler. Moreover, we will connect data bus lines from D7 to D0 of the Falcon A to the 8-bit data bus of the printer, that is, physically pins 2 up to 9 of the printer cable, and we will leave the other data lines from D8 up to D15 would not be connected. Since Falcon A uses the big endian format, this will make sure that the low byte of CPU registers will be transferred to the printer. You may recall that these bytes will actually be mapped on the addresses 39 hex, 3B hex, and 3D hex. The logic diagram of the address decoder is shown in the figure. Note in this figure that the 8 input AND gate uses only 6 address lines, A0, A3, A4 onwards up to A7. 2 inputs unused are tied to logic high, logic level 1. The address lines A1 and A2 are used as an input to the next 3 AND gates and would select one of the 3 logical ports mapped onto address 56, 58, and 60, all in decimal. As an example, when A1 and A2 both are logic low, that is 0, the address would correspond to 56. Then if we have A1 as high and A2 as low, it would correspond to address 58, and with both high we will get address mapped to 60. Today we have considered an example of mapping an input port and discussed the decoding of the address. Then we also discussed the memory mapped I/O with reference to our Falcon A processor. We also went into some discussion of the data bit multiplexing, and we tried to economize on the address space, and we just tried to utilize all even as well as odd addresses. Finally, we had defined a generalized generic I/O interface where we could connect a general I/O device with a set of contiguous addresses from the CPU. This may both be memory mapped as well as non-memory mapped. That has no bearing on the mapping of the generic I/O ports. Now we also discussed one example of a typical interface that is used for present day printers, and that is a Centronics interface. This is an appropriate moment to stop for today. Next time we'll continue with other example of I/O interfaces and would continue our discussion for the generalized I/Os. For today, it's all. Till next time, Allah Hafiz.